Let's talk about this GPS technologies. The GPS technologies is a satellite-based navigation systems that are satellites that move around the Earth, and these GPS satellites will continuously send signals to the Earth, and the base stations, the receiver, can receive these GPS signals and identify the locations. The accuracy is quite good, it's improving, and the latest value is in terms of a few meters, and it operates 24 hours a day and continuously across all the countries in the world. So GPS signal is affordable. Nowadays, almost all mobile devices are equipped with a GPS receiver, and it does not require any special antenna or a big antenna that transmits the signal back to the space. GPS receivers only receive signal from the space, and therefore the GPS receiver unit can be very tiny. And they make use of a method called triangulations to detect the positions of the objects. By knowing the positions of a few satellites, and by measuring the distance between your point and the satellites, then the locations of your point can be detected. Let's see the video how it operates.
That incredibly uncomfortable feeling you get when you realize that you're totally lost. For example, in the woods like this, or on the open ocean, or in an unfamiliar city. With the global positioning system, you can know exactly where you are anywhere on the planet. All you need is a small handheld receiver like this. The system that makes it work is absolutely amazing. There are 24 GPS satellites in orbit. They fly at an altitude of 11,000 miles, and there are always 6 or 7 of them overhead at any time. To find your location, your receiver figures out exactly how far away it is from at least 3 overhead satellites. Then it uses a little trigonometry. If you intersect 2 spheres, you get a circle. If you intersect 3 spheres, you get 2 points. The Earth is a sphere, so if you have only 3 satellites, you can use the Earth as one of the spheres. Since most GPS receivers have maps built in, you can use your longitude and latitude to find your way out of the woods, to the shore, or to your favorite restaurant. So that's how a GPS receiver works.
So the satellite will send out a signal to you, and the time delay multiplied by the speed of light will be the distance between you and the satellite. So let's say the time difference is 0.09 seconds, then multiplied by speed of light, which is 300,000 kilometers per second. Then the distance between your mobile phone and the GPS satellite is about 27,000 kilometers. So if your mobile phone can detect at least 3 satellites, then you can find out your positions by using the method of triangulations. Different satellites will have different arrival time of the signals to your mobile phone, and then the distance will be a little bit different. Because the locations of the GPS satellites is known, then you can, based on these informations and using some geometry, to find out the locations of the mobile phone. Therefore, we have 3 equations. We want to find out x, y, z, which is the 3D positions of your mobile phone, and we need 3 equations to solve 3 unknown, and therefore we need 1, 2, and 3 satellites informations to give us the distance. However, there is some problem, and we call the clock bias. So clock bias means that when the operators relied on the receiver clock to do perfect synchronizations with the satellite, however, the clock informations cannot be exactly the same. So there may be a very tiny error, talking about 1 microsecond, then it may already create a 300 meters of error. Okay, because when we're traveling at the speed of light, 1 millionth of seconds, 1 microseconds, is already 300 meters. So this error is not acceptable. We need to improve the accuracy. And it can be done by using the signal from the 4th satellite. So if we treat that error as the fourth unknown. Then if we can get another signal from the fourth satellite, then we have 4 unknown and 4 equations. Then we can also solve the equations like this. Okay, x, y, z is the 3D parameter that we want to determine, and this error is unknown, the clock bias. So we need 4 satellites informations to help us to improve the accuracy. In fact, most of the mobile phones can detect more than 4 satellites. It depends on the positions of your phone on the Earth. Whether you are at the equator or at the polar region, or in Beijing or in Sydney, depends on which part of the world you are located. This animation shows the number of satellites that you can see on the Earth. You are now locating in the northern hemisphere. The satellites that you can see are shown in the black color. At this moment, you can see 9, 10, 9, 10, 9, 8, 9, 10, and so on. Number of satellites that are moving around you, while the satellites shown in red color are those behind you. There are 2 frequencies being used by the GPS system. One is for the civilian use, is 1575 MHz, and the other one is for the military use, is at 1227 MHz. So we use different frequency for different purpose, and the GPS receiver a passive device. It just receives signal from the satellite and does not need to transmit it back to the satellite. So we rely on the signal sent from the satellite to determine the distance between the satellite and your mobile phone. But can we send a signal like this from the satellite to your mobile phone? If we do so, then how can we determine which is the starting waveform, and how can we determine the time travels? It's very hard because all of these waveforms are almost identical. Therefore, we need to do certain kinds of modulations to send out a special pattern from the satellite to the mobile phone, so that in the receiving side, you can identify or match which waveform is the first one, and then find out the time difference between the transmitted waveform and the received waveform, so that you can determine the distance between you and the satellite. So once we determine the distance between you and the satellite, then there is an algorithm in your mobile phone that can calculate the positions of your mobile without any interventions by the operators. So don't worry, your phone data will not be sent back to the US government and to calculate your positions. It doesn't need to do so. As long as your phone can determine the distance between all these satellites, the phone itself, under the certain algorithm, can calculate its locations without sending the locations back to anyone. There are 3 major components in a GPS system. One is the satellite, the second is the control segment, and of course, very important, is the GPS receiver, your mobile phone. For the GPS satellite, there are altogether 24 satellites running above us in the space, and 21 of them are active satellites and 3 of them are spare, and they are running in 7 orbits. The altitude of those satellites is about 20,000 kilometers above the Earth's surface, and they are traveling at a speed of 3.87, almost 4 kilometers per second, very fast. The satellites are running in 7 orbits. Each of those orbits are separated by 60 degrees. There are 6 orbits run through the North and South Pole. In each orbit, there are 3 satellites. There are 7 orbits altogether, and there are 6 orbits running through the North Pole and South Pole, and the 7th orbit will be the equator. So altogether, there are 3 satellites in each orbit and 7 orbits. So there are 21 active satellites in total. And the spacings among the satellites in the orbit is perfectly arranged that they are separate approximately 120 degrees apart. So in a circle, in an orbit, where there are 3 satellites, each of those are 120 degrees apart. So we can then make use of a computer model to determine the position of all these satellites in real time, and then find out the positions of the satellites using geometry, and therefore when we know the distance between you and the satellite, your positions can be calculated. So the primary functions of the satellite is, in fact, it sends you the timing informations, not the location or distance informations. It sends you accurate atomic clock informations, which is moderated so that you can find out when is the starting time of transmission, when is the receiving time of your transmissions, and then you can decode the signals, turn into distance, and then find out your positions. And as long as at any time you can see 3 satellites, and then you can make use of these satellite positions to determine your positions. And usually you can observe more than that, as shown in the animations. So the satellites will then move from the North Pole to the South Pole, and then North Pole, South Pole is around the world. So that at any time, at any positions in the world, you can see, usually talking about 5, 6 or 7 satellites at a time. And regarding the control segment, there are 5 control segments. One in Hawaii, in the US, and also a few in the islands in Indian Oceans, Atlantic Oceans, and Pacific Oceans. All these control segments on the Earth along the equator regions can control almost every single satellite. So the functions of the control segments is to send control signals to those satellites. When, let's say, some satellites may drift from its original orbit positions, then it needs to send the signals to the satellites to control it to move a little bit back or forward, so that it maintains the constant distance with other satellites. And sometimes it also need to send out the control data to the satellite to do some adjustments and corrections. On the receiving side, the GPS receiver antennas will receive the signal and amplify it, and also remove the signal noise and feed into some parallel set of delay lock loop. And this delay lock loop will be able to detect the signals from multiple satellites and check them simultaneously. So delay lock loop can also be used to find out the time differences between the time when this signal is sent out from the satellite in the space until the time when it is received by the handset on the Earth. So the different antennas surrounding you will send through signal, and it can be detected simultaneously. Then you can measure the distance between you and all these satellites and determine your position. However, there may be some possible error, such as multipath error. When you are standing in front of a tall building, especially those tall buildings with the reflective glass, then the signal may be reflected from the surface of the tall building and sent through a reflected wave. So you will pick up 2 satellite images. One is the direct signals from the satellite, and other one is the reflected signal, just like a mirror. On one hand, you receive the direct signals from the satellite, and on the other hand, you also receive a reflected signal reflected from this building. So effectively, you can receive 2 signals with a small path difference. So this small path difference will, as a result, add together and then introduce error. So your system may be either consider that you can determine 2 satellites from the space, which is only one from one source. So the consequence is that it may introduce error up to, say, a meter or half meter or the worst case is that it may not be able to recover the signal at all. Okay, so after we discuss the design of the GPS navigation system, which is a US-based navigation system, let's talk about the navigation system developed by mainland China. The navigation system developed by China is Beidao. The first version is Beidao 1, which can cover the territory in mainland China, Hong Kong, Macau, Taiwan. And the second generation's Beidao 2 can expand the coverage to the Asia Pacific area, including like Philippines, Thailand, or even as far as India and Australia. And these have been already implemented in year 2012. And in this year, the plan is to expand the coverage to everywhere in the world. Okay, the whole world can receive the Beidao signal. So operating principles in Beidao is quite similar to the GPS system in the US. There are satellites above us in the space and send signals to the ground level. But there's one difference, is that on the ground level, when you want to determine the positions of this handset, it will send out a request. And the ground stations can, based on the information from all these satellites, to calculate the longitude, latitude, and also the altitude, which means the height of your positions, according to the relief map. For example, you are in the top mountain in Huangshan, then you can determine how high your position is above the sea level. Compared with the GPS signal, it can only give you a 2D positions, only give you the longitude and latitude. But for Beidao, it can also, based on the relief map information, to give you the altitude information as well. So this is the distributions of the navigation system between the US and China. The GPS satellites are running at a lower orbit. And for the Beidao system in China, they make use of both low orbit and the high orbit. This high orbit we call the geostationary orbit, which means that at any time when you look up to the sky, the positions of the satellite looks like stationary. In other words, it's moved at the same angular velocity with the movement of the Earth. And there are two levels of services. One is for the civilian use, for the general public, and the accuracy is about 10 meters or few meters accurate, and the synchronization clocks can be as accurate as 10 nanoseconds. And there is another service for the government use and the military use. This is the frequency spectrum that occupied by different navigation systems. So the green color is US GPS system, and then this purple color is the Galileo system. Galileo system is the navigation system developed by the European Union. And the red color is Beidao, which is the system developed by China. And you can see the GPS system has already occupied some specific spectrum, and for the remaining spectrum is now being computed by Galileo and Beidao. Okay, there are some overlapping spectrum here. So regarding the overlapping of these spectrums, there are pros and cons. On one hand, it's good because it can simplify the receiver design. The similar antenna that can receive the same frequency band can be used for both systems. But it also arises competitions among the European Union and China on the spectrums. They are fighting for the usage of this particular frequency spectrum. According to the International Telecom Union, so whatever the first nations that broadcast the frequency in public at that particular domain can have the priority to use this frequency for the whole world. Okay? Therefore, now appearing that the Chinese radar system is now getting into this E1, E2, and EB5, this E1, E2, EB5 frequency spectrum, and now they are competing with the European Union catalog system. And it seems that because in recent years, mainland have launched many beta satellites in the space, and while the European Union in terms of the development of catalog is not that fast, so some of these spectrums is now being allocated to mainland. Apparently, the Chinese beta system is developing quite fast in the past few years. A number of satellites have been launched to the space and now occupying E1, E2, and EB5 spectrum in the frequency spectrum. Okay? And so compared with the catalog satellite systems that developed by the European Union, so China has the primary right to use this frequency. So let's see how the technology competitions between the US, European Union, and China will continue, and let's see whether or not the beta technologies can be more popular in the future and help to enrich the functionalities of 5G development in China.